Okay guys, so in this section we're going to start graphing the trigonometric functions that we've defined in our previous sections. So we're going to start with sine and cosine. These two trigonometric functions are going to have a lot of similarities. As a matter of fact, they are almost identical except for a horizontal shift that we'll talk about. But we're going to start with the sine function. We'll start with the parent function here, y equals sine of x. And we'll start plotting some points to sort of get the idea of the graph of this function, how like the curve looks like. So for that, we're going to refer back to our unit circle here. So let me start by labeling some, setting up my scale here. So I'm going to say this is -1, this is 1, and say that's pi right there, 2 pi. Now, if this is pi, I'm going to say this is pi halves, right? And from here, I can break it down or plot a few more points here. So I'm going to make this be my pi 4s, right? And I think we have enough to get started. Now, if we refer back to our unit circle, if you recall from the previous session, we have all the known angles here in radians and degrees. So we're setting everything up in terms of radians here. So in our graphing here, all of these are radians. So we're now consider these to be the x-axis. So it's going to be the input of the function, my x, right? And that's my y. And we're going to start plotting some points here. So as we take this function takes some inputs here, what are the outputs here? And we'll start plotting those points here, those order pairs. So we'll start with 0 here. Yeah, so if we go back and look at our unit circle, 0 is sine of 0. And again, remember sine for us is the y coordinate. So sine of 0 is 0, right? So back our graph here, we have sine of 0 is 0. So we put a point there. Now, I'm going to do a few of these and then hopefully you'll start seeing the pattern. So if you're looking at unit circle, just follow along there. If you look at a unit circle and look at sine of pi halves, sine of pi halves here, right there. Sine is the y coordinate. We're looking at just the y coordinate. So that's 1 right there. We go back to our graph. At pi halves, we're all the way to 1. Okay, so if you keep doing this, reading these values, the y coordinates from the unit circle, we're going to get some points here and then hopefully get the idea of the graph. You keep reading at your unit circle, sine of pi, if you read it there, it's 0 again. So we're back at the x-axis there. If we wanted to do sine of 3 pi halves, just right there, that's actually going to be -1. Again, we're reading back at the unit circle, just confirm all those answers, all those points. And then at 2 pi, sine of 2 pi, we're back at 0. 2 pi, remember, is the same thing as 0. Now, we have some points here. We can connect this, but I don't know if this is smooth or if it has sharp turns. For that, you can always graph a few more points. So if we do some points in between, 0 and pi halves, like pi 4s. Sine of pi 4s, it's actually square root 2 over 2. If you put that in the calculator, it's a little bit more than half. Now, if you do sine of pi 6, that's actually 1/2. If you do pi 6 right there, 1/2. And then if for completion here, we want to do the pi thirds, sine of pi thirds, it's a little bit more than square. So if you look at unit circle, sine of pi thirds is square root 3 over 2, right? So then that's more than definitely square root 2 over 2, which is more than 1/2. So we're increasing as we're going from 0 to 90 degrees or pi halves. So back in here, you'll see a gradual increase here all the way to this peak here at pi halves. So hopefully you get to see that. And if you were to do all the other angles in between here, you'll actually start seeing a pattern that way and you start getting something that looks like this. I'm going to try to roughly connect those dots. So something very smooth like that. And you get this wave-like function. And you get here this wave shape, which represents here, as it turns out, is going to represent the one cycle or one period of this sine function. Now, as we mentioned on the previous section as well, towards the end, that all of these trig functions are going to be periodic. And what does that mean? It means that they're going to at some point start repeating. There are a certain period, which in our case here is 2 pi, they'll start repeating. And you can see that from the unit circle because we've done all the values here around the unit circle. And once we got to do pi, it's going to start repeating all over. again. That would mean that this wave is going to start repeating as well. So if you were to keep going here with the x, right, this keeps going that way to infinity, and also the other way around. Keep going this way, you can see this wave going this way forever and never on both directions. This is the graph of the sine function, and it's going to be very characteristic because of this wave shape. But this is basically the idea. I mean, once you know how one cycle, one wave looks like, then the rest is going to be the same, right? They're going to start repeating. Now for cosine, the cosine function is going to be follow very similarly to sine. If we were to plot some points just like we did for sine. So if you look at unit circle here, we start with 0 here, and just like we did for sine, you look at cosine of 0, and cosine we're looking, instead of the y coordinate, we're looking at the x coordinate. So if you look at sine of 0, the x coordinate is 1, so cosine of 0 would be 1, right? And so forth, right? Cosine of 90 degrees will be 0. We're looking at the x coordinate now. So using unit circle, we can start plotting in some points in here. So we said at 0, we're going to start here at 1. At pi halves, we're at 0. If you keep going, at pi, you're at -1. At 3 pi halves, you're at 0. And at 2 pi, you're back at 1 here. And again, very similar to sine. You can start filling in some more points in there, but I think you're going to get the idea. And once you do pi 4s in there, and then the pi 3rds and pi 6 right to the side, it's going to have that same shape. Now again, just like sine, again, we're going to, if you keep inputting values after 2 pi and before 2 pi, this wave is going to keep going, and it's going to repeat that cycle over and over again. Now notice here, if you compare the two, they're really identical, except that they have a different starting point. Given parent functions here, one starts at the origin right there, the other one starts right here at the peak at 1. So that's basically the only difference here graphically, right? And then we're going to talk about the different characteristics that they have. Okay, so some of the characteristics they're going to share is that they both have the same domain, same range. So in the case of sine and cosine, as you can see in the graph, there's no restriction on the domain. Everything is allowed here as an input, because look at the x-axis here. This goes in both directions to infinity. So everything is defined there for the domain. So we'll say all reals, or negative infinity to infinity. And then the range, notice how both of these have the same peak, the same maximum, and the same minimum, so which happens to be a -1 and 1. So then, and that's inclusive, there's no holes in here. So then your range is going to be for both, it's to be the same, -1 to 1, if you look at the y-axis here. So there's nothing below -1, there's nothing above 1 here, so that everything in between, inclusive, would be the range, -1 to 1. Okay, something different here would be the symmetry. And this goes back a little bit to what we said at the end on the previous section about even and odd functions. So remember, if you remember your even and odd functions from your algebra course, you could, and we also mentioned this, we said that this function right here, sine function, was an odd function. What that means is, if you evaluate sine of -x, that's equal to negative the sine of positive of the x. So sine of -x is equal to negative sine of x. That's what it means to be an odd function. In terms of the graph, it means it's symmetric about the origin. So if you fix this origin right here and you turn your whole graph 180 degrees, that should give you the same graph, the same curve. If that happens, then you know you have an odd function. Then on the other hand, cosine is an odd function, which means if you take cosine of a negative value, or cosine of -x, then you actually have the same thing as cosine of x. So that's what it means to be an even function. And graphically, that just means it's symmetric about the y-axis. So if you were to rotate this y-axis, or pretend you can rotate the whole thing, you actually get the same thing. You can see that, right? If you, the left side is a mirror image of the right side. So this is what an even function would give you. For an odd function, symmetric about the origin. For the even function, symmetric about the y-axis. We're going to start looking at the general equation of the sine and cosine function. I say sine and cosine because they're both, it's going to work the same for both of these. So just for the sake of not being repetitive here, I'm going to stick with sine for right now, but this whole thing applies to cosine as well. Because they're so similar, and we've already seen how their graphs look like, and we know that these are functions now. So then we can apply or all the transformations that we typically apply to functions, and this is a different kind of function, a transcendental function, but it's no different than any other function in terms of being able to apply transformations on these functions. The rigid and the non-rigid transformations. So we're going to be seeing those and discussing those in terms of the general equation here. So the general equation for these two functions is the following. So here we have it. We have f of x is equal to a times sine of bx minus c plus d. Notice how we have four parameters here that we're going to be discussing, from which all our transformations are going to come. If you remember how your transformations worked, you can, from your algebra course, you can sort of identify what this A, B, C, and D are doing. There's going to be some vertical and horizontal shifts. There's going to be some vertical stretching, some horizontal stretching or shrinking. So those are the things we discuss. Now here for this particular function, sine and cosine, we're going to have new names. Right, we're going to change the names a little bit there, but they're pretty much the same transformations that we've had before. Okay, so here we have the different attributes of the function here. First of all, we have the amplitude here, and we're going to be talking about all of this in an example. But amplitude is basically going to be this coefficient, this number in front of the sine or cosine. And it's going to be the absolute value of it. So we'll talk about the sine, what the sine will do, but the amplitude itself is just going to be absolute value of this a. Period is going to be 2 pi over b, and we'll see y is 2 pi, and this b here is basically going to determine that period, how long it's going to take a whole cycle, a whole wave to complete there. And we're going to assume b to be positive, and we'll talk about what to do when we have that b equal to zero, negative, a number. So we'll deal with that. And then we have the phase shift, which is just really another name for the horizontal shift, and that is c minus b. This c minus b. And then finally this d at the end here is just the vertical shift, which is going to also determine our midline, and we'll talk about that as well. Now again, remember, this works the same for sine as well as for cosine. So whichever one you have here, you just have to remember how they look like originally, right? So remember, sine starts at the origin right here, goes to cycle all the way to 2 pi. Cosine starts at the peak at 0, 1, and then it goes that way, ends at the peak right there at 2 pi. As we'll see, so these, you can deduce here from the graph that both of these have period of 2 pi. Why? Because it takes 2 pi for a cycle to complete here. So notice how it starts at 0, ends at 2 pi. That's the whole cycle of pi of sine. And then same thing for cosine. This section in the solid red is one cycle, one wave of cosine. And then it starts repeating again on both sides. So, but it still takes 2 pi for a whole cycle to complete. So this is why when you're computing the period here, you're going to start with 2 pi because the original is 2 pi. Right? That's the reason. And then of course, you know that anything, if you multiply x, this input, by some constant here, that's going to affect that's, you know, the period here, because you'll either stretch it or compress it, right, horizontally. So that's, if you recall that from your transformations, that's what that B will do. So we can do that. Okay, so let's look at an example here, and that involves all the different transformations here, all the parameters ABC. So when you get a function like this, the sine or cosine function, the first thing I like to do is go ahead and identify all your parameters here. So this is your A, it's 3 right here is your A, this is your B. Now your C is actually negative, because this is minus negative pi. So this will be your C right here, just the negative pi. So this is one of the things you gotta be careful, because if you look at the original here, it has a minus there, and we only take the C, right? We don't care about the minus. So if you have a plus, you gotta do the minus negative. So that means your C is negative pi, and then your D is negative 1. That's your D right there. Again, your C is always the opposite of what you see there, the way we define this. So that's your C right there, negative pi. So then once you identify the 4 parameters, you're able to find the attributes here. So we'll start laying all the things here. So amplitude, I'm going to start writing what we have. The amplitude is going to be the absolute value of 3, which is just 3, right? So in this case, that's just pretty simple. Period, you have that is 2 pi over B, which is B for you is 2. So therefore your period is just pi. So in the same way, we have the phase shift is negative pi over 2, because we have C over B. C is negative pi, and then our B is 2, so we have it there. And then our midline, which is really just a vertical shift, is going to be 1 unit down, which a midline, we'll see it in the graph in a minute, that is the line that goes through the middle of the wave. That's why we call it midline. And it's going to be this line right here. As you know, a horizontal line, the equation of a horizontal line is written as y equals some constant, but y equals this negative 1 in this case is going to be our midline, which is the line that goes through the middle of the wave, as I said here. So notice here in the original one, there's no D, so 0. So then y equal to 0, which is the x-axis, is the midline. So you see how the x-axis is the middle, is the line that cuts this graph in half. It goes through the middle. Well, if we have a vertical shift, that thing is going to shift as well. So then that it's going to help us to graph that midline. Graphing this midline is going to help us have a sense of where our wave's supposed to be. Okay, so we have our XY planing here, and we are ready to graph it. Now we have our XY planing here, and we are at this point ready to graph. And I typically start by graphing my midline first, because this is going to give me a sense of where the middle of the wave is. So if you see y equal to negative 1, which came from that D right there, the vertical shift, I'm going to trace a midline, and I'm going to do it, since that's not part of the graph, I'm going to make it dash here. So through negative 1, y equal to negative 1, we have the middle of the graph is going to, or there's going to be a line, imaginary line going through there. Okay, so I graph my midline first, right? And next, I'm going to figure out my starting point, right? Now, we've seen how sine looks like in cosine. So we're graphing sine here. So think about how sine is going to look like. Looks like this, right? Where the midline just goes through it. So I'm starting at the midline right there, and I'm ending at the midline, if you remember the parent function here. Now, but I need to figure out whether I have a horizontal shift or not. And that is our phase shift right here. So then we do have a horizontal shift. The phase shift is negative pi halves, and I've already gotten my scale here. So I said I label this to be negative pi halves, and I'm going to start right on the midline. So I'm starting right here. I'm going to do this in different color here so you can see it. So right on the midline at negative pi halves is my starting point, right? From that point, we're going to go 1 period to our ending point. So remember, the period is the horizontal distance that it takes the whole wave to complete, the whole cycle. So I know I'm starting at negative pi halves right on the midline, and I'm going to end right on the midline, finish right here, right on the midline, according to my graph of sine. But where though? Where in the x-axis? So for that, we need the period. And we computed the period to be pi. So then we're going to go pi from this point right here. From negative pi halves, we're going to go pi. So if you add pi to negative pi halves, you can see how pi will end up right here at pi halves. So it's going to look very symmetrical here. I'm going to end right there. And I'm right on the midline as well. Now, once you have your starting point and your ending point, you want to go ahead and, because if you recall here, let's go back for a minute here, for a second here, to our original function, y equals sine x. Remember how they all going to look the same. The period was 2 pi, 0 to 2 pi right here. But then right at halfway, so right at pi, we were crossing the midline again. And then on pi halves, on the first quarter of the way, we're at our peak. And the 3/4 of our way, we were at our minimum. The same thing is going to happen here. We just have different values, and everything has been stretched or compressed depending on which function you're doing. So at this point, I like to, once I know the span of the one period, I like to take that interval right there from negative pi halves to pi halves on my midline. I'm going to split it in 4 equal subintervals. So right there. So in this case, this one turned out to be pretty easy, pretty straightforward. You can clearly see where those breaks are. You don't need to label those. I mean, as long as, because we're going to try to graph this as symmetrical as possible. So you can see this is negative pi 4s right there, negative pi 4s, and this is pi 4s, right? The point is to just have 4 marks right there, or 4 subintervals, equal subintervals, so that we'll know where to turn to make it as accurate, as smooth as possible here. So from here, the only thing left here for us to use is the amplitude, right? Because we want to know how high and how low we're going to go. The amplitude, remember, is this A here, and that's the vertical stretch. If we go back to our original here, the original has an amplitude of 1, right? Because there's a 1 in here, understood? So if we have a larger number there, so we're going to stretch this whole thing vertically up and down. So our max and our min are going to change. So that's what's happening here. Now remember, this is going to happen from the midline. That's why it was important to have the midline there. I don't want you to think that it has to go from the x-axis. Happen to be the x-axis here because the parent function has the x-axis as the midline. But that changes if you have a vertical shift. So we do have a vertical shift. We went a unit down. So then the amplitude is going to be the distance from the midline to either peak, whether it is the max or the min. At the first quarter of the way, I'm going to be at my max, and my max is going to be 3 units from the midline. The midline is a -1. So then my peak is going to happen right at 2 right there. And then halfway, I'm back at the midline, remember? And then 3/4 of a way, that's why I made those marks right there on the midline. I'm 3 units down from the midline. So if the midline is at -1, I go down 3 units to -4. So I'm right here, roughly. And then finally, I'm back at the midline where I'm going to end my wave. And then you already know the shape of this wave, so you just try to make it as smooth as possible here, connecting those dots. So we're not going to make any sharp turns. We're going to turn right there at the peak, get back to the midline, turn, and back at the midline. And there it is, our sine function there, our sine wave. Okay, as you can see, I mean, that's just one period of the function, right? So of course this keeps going forever to the left and the right. But if we were just graphing one period, which is what you would normally be doing anyways, this is how the one period looks like. Okay, so here's an applet that you can use to kind of graph these things quickly, and also, most importantly, compare them. It's a really simple, nice applet. You can change this to degrees or radians. So I'm going to do it radians. We're doing all this in radians. We're doing sine. And you can change all the parameters here, the A, the B, the C, and the D. Now notice how they have a plus C here. So that means we have to put the actual C in here, right? So that's a little bit different, but it will still work. Notice how if we enter all from the previous example, we enter all the parameters, right, that we had. And we had, what was it? Negative pi was our c, and we had a vertical shift of -1. There it is. This was our function right there. As a matter of fact, well, it was plus pi, I believe. So let me change that. Okay. So this was our function there. If you click at this in this box right here, so if you compare it with the original function, that one in red is the original. You can see how this, right, has been compressed. The green one has been compressed. So that means the period is a lot smaller than the original 2 pi period. In other words, it's actually cut in half there, so that you can fit 2 waves in the period of 2 pi. You can see a horizontal compression, you see a vertical stretch, you see all the shifts. So you can quickly see, and this, the nice thing about this applet is that you can kind of play around with the parameters here without having to spend all that time graphing this by hand. But you also need to know how to graph this by hand. All right, so hopefully this helps you see and compare a sine function to its parent function and be able to see all those transformations along with it. Okay, a couple more things is we didn't discuss what the negatives would do, and we will have to do more examples, but just quickly here, if we had a -3 for A instead of 3, then the wave, if you recall that from your transformations in your algebra course, would be reflected across this midline right here. So it will have a reflection here, and it will look like this. So instead of going to your maximum, you'll be going to your min first, and then you go to your max after the halfway point. You start getting to your max. So basically, you just reflect it over this midline. That's if you have the A negative, right? The amplitude still the absolute value, so still 3, right? So you still go 3 units up and 3 units down, but it's just the graph would just be flipped here, would be reflected. Now, if the B is negative, so when we define here, we assume B is positive, then that's when you want to that's when the even and odd comes in handy here. So if you're doing sine, you can bring that negative out, right? Bring the negative out, and then that will mean a reflection anyways. Or if it's cosine, then you can just ignore it. You don't have to, because cosine is an even function, so that if you have a negative b here inside of a cosine function, because it's even, it actually makes it a little bit easier. You can ignore it, that negative. Now you gotta be careful there when you have a c though, because that applies to the whole thing here, so you may have to factor things out before you can either ignore the sign or pull it outside. So that C may change if you do in fact have a C. So then, we will investigate those kind of things with more examples. But this is the procedure of how to graph a sine or cosine function.